Welcome to another deep dive. You know those AI systems that can, like, write poems and answer all your questions?
Oh.
Well, today we're going deeper. We're going to explore how LLMs actually represent concepts.
Yeah, based on this super cool research paper, The Geometry of Concepts.
Sparse Autoencoder feature structure.
Yeah, that one. It's like a deep dive into the mind of an AI,
Oh, I like that.
revealing this hidden landscape of concepts.
Okay, so give me the picture.
So picture this vast concept universe.
Inside the LLM.
Yeah, every idea is like a star in a galaxy.
Whoa.
And this research uses a technique to map this uncharted territory.
What's the technique?
They call it Sparse Autoencoders, SAEs.
SAEs.
Think of it as like a 3D map. Each point is a different concept.
Okay.
And just like our universe, this concept universe has structure at different scales.
So it's like, I don't know, the solar system, the galaxy, and the universe.
Exactly. The paper explores 3 levels.
Okay, love it.
We're going to start with the atom scale, where like simple relationships between words might be hiding. Then we'll zoom out
Okay.
to the brain scale. And then finally to the galaxy scale.
So start me off at the atom scale. What are we even looking at?
So imagine tiny crystals hidden within this vast cloud of concepts.
Crystals, like physical crystals.
Not literally, no, but each crystal represents a simple relationship between words.
Okay.
Kind of like an analogy, the classic example. Man is to woman as king is to queen.
Oh, right. Like, I get the analogy, but how do you find these crystals in the data?
Right. So each concept in the LLM is represented by a point in this like high dimensional space.
Mm-hmm.
Researchers can calculate the distances between those points.
Okay.
When they look at the points for man, woman, king, and queen, they actually form a parallelogram.
Oh, that's so cool.
Yeah. The really cool part is the direction and distance from man to woman is the same direction and distance from king to queen. That consistent shift that represents the concept of female.
So the LLM learned this relationship on its own, even though no one programmed it.
Exactly. And that's one of the most mind-blowing things about this.
That is really cool.
But there's a catch.
Uh-oh. What's the catch?
These crystals aren't always easy to find.
Oh, okay.
They're often obscured by what researchers call distractor feature.
It's a distractor feature.
Think of it as noise in the data.
Oh, okay.
So it could be something irrelevant to the meaning, like the length of a word.
Okay, so how do they filter out this noise?
They used a statistical technique
What technique?
called linear discriminant analysis, or LDA,
Okay.
to filter out the noise and reveal the crystal patterns.
Oh, that's interesting. Did they find any particularly interesting examples?
One that stood out was the relationship between countries and their capitals.
Oh, wow.
So Austria and Vienna and Switzerland and Bern,
Okay.
they form a nearly perfect trapezoid. The direction from each country to its capital, well, that represents the concept of capital city.
It's like it's learning geography.
Exactly.
Wow, what does this even tell us about how LLMs work?
So finding these crystals suggests there's an underlying structure and logic in these LLMs,
Okay.
even if we don't fully get it yet.
Makes sense.
It's like a step towards understanding how they're able to reason, how they connect ideas.
Wow, so these tiny crystals are really a big deal.
Oh, yeah, definitely.
But I bet they're just the tip of the iceberg. I mean, this concept universe has to be much bigger.
Well, yeah, way bigger.
So what happens when we, like, zoom out? When we look at the bigger picture?
That's where things get even more interesting.
Okay, I'm ready.
We move from the atom scale to the brain scale,
Brain scale.
exploring whether the LLM might be organized like our own brains.
Hold on, you're saying LLMs might have brains? Like actual physical brains?
Not physical structures in the way we have brains, but more about how the concepts themselves are organized and connected within the LLM.
Okay.
Remember those SAE features?
Yeah.
Think of them as the building blocks of concepts. By analyzing which features activate together, you can see which concepts are related in the LLM's mind.
So they're looking at, like, groups of features that light up together.
Exactly. And they used a method to identify these clusters of features.
Okay.
Think of it as like identifying neighborhoods in a city
Okay.
where people with similar interests live.
Oh, okay. I like that analogy.
And guess what?
Right.
They found distinct lobes, just like in a brain.
No way. So certain areas of the LLM are, like, specializing.
Yeah, it seems that way.
What kind of specializations are we talking about?
One of the most striking findings was a lobe heavily focused on code and math. It's as if the LLM had developed a separate math brain.
Well, that's wild.
They found other lobes that seemed to specialize in different types of English text.
Like what?
Like one for short messages or dialogue and another for, like, scientific papers?
This is blowing my mind. It really does sound like an LLM is organizing its knowledge, like in a brain-like way. Did they expect this, or is this a total surprise?
Total surprise.
Wow.
Not only were these lobes functionally distinct, but they were also spatially localized.
Spatially localized?
Yeah, they weren't randomly scattered. They actually occupied specific regions, which is a huge discovery.
Wow, so it's like even more organized than we thought.
Yeah, way more complex.
Okay, so but before we get ahead of ourselves, did they do anything to confirm that these lobes weren't just a coincidence?
Of course, yeah. They used statistical tests to confirm the relationship between feature activation and location was statistically significant.
Okay, so it's not just random. This is like solid science we're talking about.
Oh, yeah, absolutely solid.
Okay, so we journeyed through the atomic level with those crystals, right?
Mm.
And now we've zoomed out to the brain level and we've discovered these lobes.
Right.
But there's one more level to explore.
The grandest of them all. The galaxy scale.
Okay, the galaxy scale. Hit me with it.
Get ready, because the shape of the LLM's concept universe might be even more surprising than you think.
I can't wait. Tell me everything.
Well, they started with a simple idea. If concepts were randomly distributed, you'd expect the concept universe to be roughly spherical.
Okay, a big cloud of concepts.
Yeah.
But it sounds like that's not what they found.
They did not. What they found is that the concept universe isn't spherical at all. It's something much stranger.
Okay, stranger's good. I like strange. So tell me, what is it?
They call it a fractal cucumber.
A fractal cucumber. I have no idea what that even means.
Yeah, it's not something you see every day. Imagine a cucumber that gets thinner as you move along its length.
Okay, I can picture that.
And then imagine that pattern repeating itself at smaller and smaller scales.
Whoa, okay.
That's where the fractal comes in.
So it's like elongated and bumpy?
Mm.
But why is it like that? Why isn't it just a nice normal sphere?
Well, the researchers found this unique shape is described by what's called a power law.
Power law, what's that?
It's a mathematical pattern that shows up in lots of complex systems.
Okay.
Like from the distribution of city sizes to the frequency of words in a language.
So this power law is shaping the concept universe. That means there must be some kind of underlying order to how the LLM is organizing information, right?
Exactly. And here's where it gets even more interesting. This cucumber shape is most prominent in the middle layers of the LLM.
Okay.
Remember we talked about how the LLM has layers, like an onion?
Uh-huh.
So it seems those middle layers play a special role.
So the middle layers are where things get cucumber shaped. What's so special about those layers?
Well, the researchers think those middle layers are crucial for compressing information and forming abstract concepts. It's like they're taking the raw data from the earlier layers and distilling it.
So as information flows through those layers, it gets sculpted into this fractal cucumber shape. Wow.
Exactly. It's like a glimpse into how the LLM makes sense of the world, how it goes from simple details to more complex ideas.
This is wild. I'm loving this. But the paper also mentions clustering entropy.
Oh, right.
What is that, and what does it tell us?
Clustering entropy is a measure of how tightly concepts are grouped together. Think of it like the density of a city.
Okay, I see where you're going with this.
In a bustling city, things are packed close together, right?
Yeah.
But in a rural area, they're more spread out. Clustering entropy measures that kind of conceptual density.
So do they find any patterns in how this clustering entropy changes?
They did, and it's super interesting. They found it tends to be lower in those middle layers.
Lower, so that means...
Concepts are more tightly clustered together.
Okay.
Which makes sense if those middle layers are forming those abstract concepts.
As things become more abstract, they get grouped together more.
Yeah, like based on shared characteristics.
Okay, so what about the other layers then?
They found the clustering entropy is higher in the earlier and later layers.
So things are more spread out.
Exactly.
Why would that be?
In the early layers, it might be because the LLM is still processing that raw data, you know? And it hasn't formed those higher level concepts yet.
Okay.
And in the later layers, it might be because it's starting to specialize even further.
Oh, okay, so like even more distinct clusters.
Exactly.
It's like watching a city evolve over time, you know?
I love that analogy.
Yeah, it highlights how dynamic and complex this concept universe really is.
It's not just sitting there. It's constantly changing and evolving.
Okay, I have to say, this whole concept universe is mind-blowing. We started with those crystals, then those lobes, and now the whole universe is this fractal cucumber. It's like we've taken a journey through the mind of an AI.
I know, right?
But as with any good exploration, we're left with even more questions.
Always more questions.
What does all of this tell us about how LLMs actually think? How they reason?
That's the million-dollar question, and the one that has researchers the most excited.
Yeah, because we've seen the map, but now I want to know how it all works.
I hear you. Well, get ready, because we're about to dive into the heart of the matter.
I am so ready.
This research might hold the key to understanding LLM's incredible abilities.
Okay, so back to this whole concept universe thing.
Yes.
Last time we uncovered those concept crystals.
Right.
We discovered that LLMs might even have those specialized lobes, for different types of thinking. But we left off on a cliffhanger.
I know.
We were about to reveal the overall shape of this concept universe.
The shape.
And you said it wasn't what we might expect.
It's not.
So tell me.
Okay.
What does it actually look like?
They call it a fractal cucumber.
A fractal cucumber.
Right.
That does not sound like any shape I've ever heard of before.
It's definitely not your typical geometric shape.
Okay, so paint me a picture.
Right.
What are we even talking about?
So imagine a cucumber.
Okay, I can picture a cucumber.
But as you go along its length, it gets thinner and thinner.
Okay.
And then imagine that same pattern.
Of it getting thinner?
Yeah, but repeating itself at smaller and smaller scales.
Oh,
Okay, that's the fractal part.
So it's like elongated and bumpy? Is that kind of what we're getting at?
Kind of, yeah.
But why? Why is it shaped like that? Why isn't it just a nice round sphere?
The researchers found that this unique shape, this fractal cucumber, is described by something called a power law.
Power law. What's a
Yeah.
power law?
It's this mathematical pattern that pops up all over the place in complex systems.
Okay, give me some examples.
Like, think about the distribution of city sizes,
Okay.
or how often different words appear in a language. That's all governed by power laws.
So you're saying this power law is actually shaping the whole concept universe.
It seems like it, yeah.
So that means there's some kind of underlying order to how the LLM is organizing information, right?
Exactly.
This is getting deep.
And it gets even deeper.
Oh, no, lay it on me.
This cucumber shape is most prominent in the middle layers of the LLM.
The middle layers, okay.
Remember how we talked about how the LLM is organized in layers like an onion?
Uh-huh. Yeah.
Well, it looks like those middle layers are doing something special.
So the middle layers are where it gets all cucumber shaped.
Pretty much.
But what's so special about those layers?
The researchers think that those middle layers are super important for compressing information
Okay.
and for forming abstract concepts.
So like taking all the raw data and making it into something more meaningful.
Exactly. They're distilling it, basically.
Okay, that makes sense.
It's like they're taking all the raw data from the earlier layers and turning it into these higher level representations.
So it's like as the information flows through those middle layers, it gets sculpted into this fractal cucumber shape.
That's a great way to put it.
Wow. It's a pretty mind-blowing stuff.
It is. It's like you're seeing how the LLM is making sense of the world.
Yeah, like going from those basic details to those more complex ideas.
Exactly.
Now, the paper also mentioned this thing called clustering entropy.
Oh, yeah. That's another key piece of the puzzle.
Okay, break it down for me. What is that all about?
Okay, so imagine you're looking at a city.
Okay, got it.
Think about how things are arranged in a city,
Yeah.
Clustering entropy is a way to measure how densely things are packed together.
Oh, okay. Like how close together the buildings are.
Exactly. So in a bustling city, things are packed in tight.
Right. People and buildings everywhere.
But in a rural area, things are more spread out, right?
Yeah, lots of open space.
Clustering entropy measures that kind of conceptual density.
Okay, so it's like, are the concepts all clustered together or are they more spread out?
You got it.
So did they find any interesting patterns in this clustering entropy across those different layers?
They did.
Okay, tell me more.
They found that the clustering entropy tends to be lower in those middle layers.
Lower, so that means the concepts are...
More tightly clustered together.
Which makes sense, right? Because those are the layers that are forming those abstract concepts.
Exactly. It's like they're creating these little conceptual neighborhoods.
Oh, I like that. Conceptual neighborhoods.
Where all the related ideas are grouped together.
Okay, so what about those other layers, the ones that aren't in the middle?
Well, they found that in the earlier and later layers, the clustering entropy is higher.
So more spread out.
Right.
So why would that be?
Well, in the early layers, it might be because the LLM is still processing all that raw data. It hasn't formed those higher level abstractions yet.
So it's still figuring things out.
Exactly. And then in those later layers, Well, maybe it's because the LLM is starting to specialize even further.
Oh, okay, so it's creating even more specific clusters.
That's the idea.
It really is like watching a city grow and evolve.
Isn't it?
Starting with those basic building blocks.
Yeah.
And then things get more complex and specialized over time.
Exact.
So we've got these conceptual neighborhoods forming in the middle layers, and then things get more specialized and spread out in those later layers.
It's a dynamic process, for sure.
It really highlights how complex this whole concept universe really is.
It's not just static, it's constantly changing.
Okay, I have to admit, this is all pretty incredible.
It's mind-blowing stuff.
We started with those tiny crystals.
Yeah.
We found those brain-like lobes.
Right?
And now we've got this whole universe shaped like a fractal cucumber.
With these unique clustering patterns, it's amazing.
It really feels like we've taken a journey through the mind of an AI.
I know, it's incredible, right?
But of course, we're left with even more questions.
That's the nature of exploration, isn't it?
So the big one for me is, what does all of this tell us about how LLMs actually think?
Yeah, how do they reason? How do they solve problems?
Exactly. Because we've seen the map.
Right.
But now I want to understand how it all works.
Well, get ready for the next part.
I'm ready.
Because we're about to dive into the heart of it all and see if this research can shed light on how LLMs do those amazing things they do.
All right, so we've seen the map of this concept universe.
We have.
We've explored those tiny crystals, the brain-like lobes, and that mind-blowing fractal cucumber shape.
It's a lot to take in.
It is. But now I really want to know what it all means.
The big question.
Yeah, does this research actually tell us anything about how LLMs think, how they reason?
Well, that's the question that everyone's asking, right?
It is.
And while this paper focuses more on the structure of the concept universe, it does offer some really interesting clues about their abilities.
Okay, I'm all ears. What kind of clues are we talking about here?
So let's go back to those concept crystals for a second.
Okay, back to the crystals.
The fact that LLMs can learn these simple relationships, you know, like those analogies.
Right, like man is to woman as king is to queen.
Exactly. That suggests they're capable of at least a basic form of analogical reasoning.
So they're picking up on the patterns and rules of language, even though no one's explicitly teaching them that.
Yeah, and that's pretty remarkable in itself.
It is. But how does that basic kind of reasoning scale up to the more complex problem solving that we see in LLMs?
Well, think of those simple analogies as building blocks.
Okay, building blocks.
Maybe by combining and manipulating these basic relationships. You know, LLMs can construct more elaborate chains of reasoning.
Ah, okay. So it's like starting with those simple crystals and building up to something more complex.
Exactly. And then remember those specialized lobes.
The ones that focus on math and different types of text.
Yeah, those. What if they're not just storing information passively?
Oh, yeah.
What if we're actively processing it?
So it's not just one big brain, but like a bunch of specialized units all working together.
That's the idea. Almost like specialized teams within the LLM collaborating to solve problems.
It is fascinating.
And don't forget about that fractal cucumber shape.
Right. The shape of the whole universe.
Exactly. The way concepts are clustered and organized in that unique way could also be playing a role.
In how it thinks.
Yeah. It could be influencing how the LLM retrieves information, you know?
Okay.
And how it connects different pieces of information.
So potentially leading to more efficient and sophisticated problem solving.
That's what we're thinking.
So it's all connected. The structure, the specialization, the way concepts are clustered.
It all seems to be working together.
To allow for these incredible feats of reasoning and creativity that we see in LLMs.
It really is like a symphony of concepts.
All orchestrated within this amazing concept universe.
A beautiful image.
It is. This has been an incredible journey, I have to say.
It has.
We started with those tiny crystals.
Uh-huh.
We went through the brain-like lobes.
Right.
And then we saw the whole concept universe take shape as this fractal cucumber.
A wild ride.
It was. But, you know, as with any good exploration, we're left with even more questions.
There's always more to learn.
What are your final thoughts on all of this? What do you hope our listeners take away from this deep dive?
You know, what excites me most is the sheer potential of all of this.
Yeah.
If LLMs are already organizing information in these complex and structured ways,
Right.
imagine what they'll be capable of in the future as we continue to, you know, develop these technologies.
It really does feel like we're just at the beginning of something truly groundbreaking.
It does.
And to all our listeners out there, if you're as fascinated by this research as we are, you know, check out the original paper.
Yeah, it's called The Geometry of Concepts, Sparse Autoencoder Feature Structure.
It might be a bit challenging, But it's worth the effort if you really want to dig into the technical details.
For sure.
And until next time, keep exploring, keep asking those questions, and never lose that curiosity.
The world of AI is full of wonders, and who knows what incredible discoveries await us just around the corner.
So well said. Thank you for joining us on this incredible journey into the LLM concept universe.
It was a pleasure.
We'll see you next time for another deep dive into the world of knowledge and ideas.